Okay, for the last portion of Chapter 6, we need to look at some more parts from learning objectives at the bottom of the very long list. We're going to look at how we can determine concentration of a species using data from what we call acid-base titrations. There are other examples that are not acid-based examples, but these are the simplest ones that we'll start with for now. To begin with, we need to explain what in the world is a titration. The titration is a procedure that we use to determine the concentration of a solution by using a measured volume to react with some other solution of another substance whose concentration is known. So the one with a known solution a known concentration is called a standard solution. In the acid-base context, we can use simple examples like this one here with hydrochloric acid and sodium hydroxide. Simple acid-base, a very ordinary stereotypical example, to be honest, for acid and base, where you're going to make a salt and water, very ordinary kind of thing. And once this reaction is complete, we can calculate the concentration of the unknown solution of something. So if we're mixing some HCl with some sodium hydroxide. One of them is known, one of them is unknown. But how do you know when the reaction is complete? What techniques do we have, resources do we have that are ready to do this? We're going to have things, the standard solution of the known concentration will be in a device we call a burette. And the flask below it will typically use an Erlenmeyer flask because it's very convenient for swirling. And it will contain an indicator solution. Perhaps you've heard of phenolphthalein. There's a variety of others. Some are just called universal indicators. Thymol blue, a bunch of variety of things are out there. Phenolphthalein actually works quite fine for an acid-base titration. And the point of it is it's going to change. It's going to change a color when the reaction is complete. Hopefully you're not colorblind and their color changes are not unfriendly to you. And here's an example of what phenolphthalein looks like. It's one of those incredibly weird spelled words. Phenolphthalein in an acid solution is completely clear. You don't see anything. But once you've added enough base until the reaction is essentially complete, the color begins to change. And when the color just barely changes, then we know we've reached a point where the reaction is complete. If you have red-green colorblind, my poor son would never get the point here. He wouldn't see it. But there are electronic techniques, analytical techniques that a person can use and still be a very successful chemist, even if you can't see those color changes. All right, now there's a general procedure here, and again, we're going to need to write the units out. Write the units out step by step and make sure they cancel. The balanced equation is very straightforward in this case because no coefficients are required. It's 1 mole of sodium hydroxide with 1 mole of HCl gives you 1 mole of sodium chloride and 1 mole of water. If you're given a certain volume of sodium hydroxide, this is going to feel very similar to what we've talked about already. We're going to use molarity of the sodium hydroxide as a first conversion factor to find out how many moles there are. But again, we always have to come back to moles. And the moles are going to be determined from the coefficients of the balanced equation using our good friend, the mole ratios. As long as you've got a balanced equation as your starting point, everything is fine. And then once we know the moles of sodium hydroxide relating to the moles of HCl, we'll need to use molarity again, or sorry, you divide by a volume, and you'll see it when we set it up. Taking moles divided by a volume will give us molarity. That's, in general, how these things are going to work, but it makes no sense until we see some actual examples. All right, ready, set, go. Let's say we've got a sodium hydroxide solution. It's 0.1 molarity, 0.1 molar, 48.6 milliliters. And we're going to take that much in our burette to react with a measured amount of our unknown HCl. Apparently they use 20 milliliters. One good way to do that is using a volumetric pipette. A volumetric pipette allows you to measure 20.0 milliliters very accurately. Volumetric pipette is just a comment, just so you know how these things are done to get that many sig figs. And so the point now is to determine the concentration of this unknown, or this HCl solution of unknown concentration. So this HCl reacts with sodium hydroxide. We know the volume of the sodium hydroxide. We know its molarity. Again, this feels like dilution where volume and molarity are going to be related with each other. And to come up with the number of moles of sodium hydroxide, using the molarity of the sodium hydroxide. We then relate the moles of the sodium hydroxide to the moles of the HCl with a mole ratio. The mole ratio from our balanced equation, which in this case is very simple, 1 to 1. And then we have to use the volume of the HCl because the moles divided by the volume will give us molarity. It feels a little funny, but it's terribly similar, and the units will make sense when you lay them out properly, lay them out carefully. All right, continue. So here, let's set this up and see how it looks. So ready, set, go. Get your pencil, get your paper, and let's think what we need to do. So we'll start with the volume of our sodium hydroxide, 48.6 milliliters of sodium hydroxide. Write the compounds in there because sometimes we're looking at the wrong things if we don't. And then we're going to use its molarity to figure out how many moles there are. But apparently we should pay attention to units and figure out whether our liters are going to be important here, but we'll get to that in a minute. 0.100 doesn't matter. Moles of sodium hydroxide, the 00 doesn't go in your calculator, per liter. And no, the units do not cancel yet, but we'll be okay in a second. You'll find out in this example. So that would give us, if we had converted the milliliters to liters, we would have moles here. In the long run, this is going to work out. Next, we need to use a mole ratio. In this case, it's quite simple because there isn't a lot to think about. 1 mole of, the coefficients are all easy too. 1 mole of sodium hydroxide reacts with 1 mole of hydrochloric acid, 1-to-1 ratio. But then from this point, you can tell that we're at least going to cancel out the moles of sodium hydroxide. And we're looking for concentration. So there you have moles. But now we have to have volume, and we're going to have to divide by volume. So in this case, we divide by 1 over, and 1 over allows us to divide. You could put it on the left, it would get you the same thing. But the 20 milliliters of your HCl and moles divided by volume. We could convert it to liter, we could have converted the other ones to liters, but guess what? It really all works out the same. And so the milliliters now fall out of this calculation, and all you're left with is moles of HCl. My tool didn't write very well, sorry about that. I'll fix it just a second. I don't like that to be in error. Okay, that looks better. So moles on the top have not been canceled, and the liters on the bottom haven't been canceled. Moles per liter, and now it's a calculator exercise. Unless you want to do this in your head, most of us don't. We'll punch it in the numbers, and it's not incredibly surprising. The digits we get here are 0.243 molar is HCl. That's the concentration. Can you predict this? Can you guesstimate? Probably not. But if you look at these numbers, it isn't actually too shocking that 486 divides by 2 effectively to give you 243. Now, this is one way of setting it up. You may not like these because they feel very, very mysterious. Again, if you write out the steps and watch for things to cancel, knowing that you're always going to need a mole ratio and a titration question, and you're always going to need molarity, keep those in mind and it'll help you figure out what you're doing. But the mole ratio is key to getting these correct because sometimes it's not 1-to-1. Another way to think of this problem is laid out on this slide. So we think about how many moles of sodium hydroxide are available. It was a standard solution. We know its concentration. We figured out how much it took in that burette. We dripped it down into the flask, and the solution of the sodium hydroxide was 0.1 moles per liter. In order to get the actual number of moles of the sodium hydroxide, we do have to do the liters to milliliters conversion. You got to get good at this one if you haven't by now. And so the liters cancel, the milliliters cancel, and the answer to this at this step is now going to be simply the moles of sodium hydroxide. The number of moles of sodium hydroxide should be equal to the moles of HCl, and so the moles of HCl reacted is going to be the same as the moles of sodium hydroxide. Using a mole ratio, that becomes more explicitly shown. And this is a molarity. We keep using these same things. And then the answer then is simply the same as the value of the sodium hydroxide. But in order to determine the concentration of the HCl solution, we start with the number of moles, and we must have to divide by the milliliters, right? We had the milliliters, but effectively then we won't have molarity until that's converted to liters. So put in your milliliters and liters conversion. Oh, by the way, I want to always make sure to see things that cancel. And milliliters cancels here, and it gets your decimals in the right place. And there you have an answer, which is precisely what we had a minute ago on the other slide. Fair enough. Not impossible. Always watch your units. Be careful to write out the steps. Watch units. If they're not there, who knows what mistakes you'll make. And write out all your steps. Taking shortcuts is a very tempting but not wise pitfall. All right, let's do one more, and then we'll say we've done enough examples for one day. The concentration, let's find, of a potassium hydroxide solution, if it takes 35.1 milliliters to neutralize 23.4 milliliters, I made these numbers up, can you guess, of 0.342 molar HNO3, that's called nitric acid. And in order to do this, what steps are required? So nitric acid is HNO3. Potassium hydroxide, you've learned how to name those compounds, so I won't write that one in for you. So step one, what do we have to do? Every single time we have to pay attention to the right steps or we'll miss something. Step one is the balanced equation. So in order to do that, let's write it out. Potassium hydroxide reacts with, I'm going to leave you space for balancing in case we need it, HNO3, nitric acid. And what's it going to make? Well, let's see. It should be potassium nitrate. We'll talk about balancing equations later with these things. And water. In this case, all the ions are +1 and -1. And so all the coefficients turn out to be exactly 1. And so this isn't a complicated equation to balance. As is, will be just fine. Then what do? So let's look at how do we have to figure this out. The same kind of idea we had before, remembering that there's 23.4 milliliters of the nitric acid solution, and we're trying to find the potassium hydroxide this time. The potassium hydroxide is our interest thing. So this time we'll start with the figure out the number of moles of the acid. So 23.4 milliliters. We're going to get around the milliliters to liters thing here gradually. 0.342 moles of HNO3. I didn't write that. I meant to. HNO3, right? And this one is per liter, but no, it's not going to cancel yet. Whoops, I wasn't trying to make that line there. Let me fix that for you. Capricious tool. And again, you use molarity, but we need the mole ratio to know how these react. In this case, again, very simple because everything has a coefficient of 1. So 1 mole of nitric acid reacts with 1 mole of potassium hydroxide. And we're looking for its concentration. Now, pay attention to what's canceling. Moles of nitric acid. And we have moles of potassium hydroxide on the top. We have liters, we have milliliters. We're not done yet because what piece of information has yet to be used? We forgot, we haven't used the volume of the potassium hydroxide. Again, this is like the previous example. So if you have the impulse that I'm going to show you that actually works out, that you need to take the moles and divide it by, we have moles of potassium hydroxide so far, relatively speaking, but we need to divide by a volume, the volume that's in this problem statement, to get molarity. And so we'll put it over here because that actually makes no difference. You could have put it at the end under a 1. That would be effective as well. But now the milliliters cancel. The milliliters here is the potassium hydroxide. And that got really messy. I apologize for this weird tool. All right, so the milliliters of milliliters cancel. And so really what you're left with is moles of potassium hydroxide and liters. And so now it's a math problem. Punch in your values in your calculator, because who's going to do it without? Not me, not you. and see what you get, and then we'll talk about sig figs. So I get an answer. Pause the recording before you watch my answer. I want you to make sure you can do it. Pause it, double check yourself, see if your calculator math is working today, see if you can verify it. I'm letting you wait. And then I get 0.228 molar potassium hydroxide. Now, can you make an estimate on these things? Not likely, but it's all right. And how many sig figs are appropriate in this answer? Oh, I bet I actually did it right for you. Notice that all of these values are 3 sig figs, from the 35.1, the 340.342, and the 23.4. Those are all 3 sig fig values. And so again, this value reported at 3 sig figs is appropriate. We are often lazy with sig figs, but it's a really good reminder to try these things as you go. All right, this would be the last example I want to put in this recording. I hope this helps you on your homework. Be careful again about write out your steps, all the steps. Be sure the units cancels. Make sure units cancel. Anyway, this should help you on your homework. Good luck studying. Ask questions as needed, and I'll see you in class.